Lesson 3.5, derivatives of trigonometric functions. Before we actually talk about trig derivatives, we're going to have to talk about a little bit of a review. So this was from Monday's material, but you should probably double check that you remember this stuff, and then we're actually going to expand on it a bit. So see if you can fill in those blanks. All right, if p of x is a position function, then p prime is the derivative, which would be a velocity function. And p doubled prime would be the derivative of velocity, which is an acceleration function. All right, double checking our comprehension of that. I've got a few questions just to check on it. Again, I would encourage you to pause each one and see if you can answer it. So pause this, read it, see if you can answer the question at the bottom. All right, I'm going to go over it right now. Let's assume P of t and Q of t are position functions, giving the distance in meters Paul and Quincy respectively are from school after t seconds. So it says after 60 seconds, P prime of 60 is 0, and Q prime of 60 is 125. Since P and Q are position functions, these are velocity functions. So I know at time t equals 60 seconds, Paul is stopped. His velocity is 0, which means he's stopped. And Quincy's velocity is 125. Quincy's moving forward. And that's going to be 125. Let's see, this was measured in meters and seconds. So it's going to be at 125 meters per second. That's pretty fast. I'm assuming he must be in a car. All right. Same thing. We still know this from previously. This was just what we answered before. Some new information, P double prime of 60 is 10, Q double prime of 60 is -4. See if you can describe what you know about Paul and Quincy from that. All right, so this is a measure of acceleration. This means Paul's accelerating at 10 meters per second squared. So he was stopped, but we must have caught him right at the moment he hit the gas pedal. You're feeling your body shoot back a bit from the acceleration, and he's just starting to move forward, right? His tires actually haven't moved yet, but you're feeling that movement, that acceleration movement. Quincy's acceleration is negative though. Quincy's accelerating at -4 meters per second squared. Since he was having a positive velocity, but his acceleration is negative, he must be slowing down. Now it doesn't look like he's slowing down by much yet. So maybe he just took his foot off the pedal. Maybe he just started pressing the brake. We don't know, but we definitely know he's slowing down. All right, same stuff, same information we knew before. Paul isn't moving, though he is accelerating. Now P triple prime is 0. We haven't talked about that triple prime and what that is, but see if you can figure it out. Same thing here, Quincy's moving forward. He's decelerating, he's slowing down, but Q triple prime is -80. So think about what that would mean. All right, so this is a derivative of acceleration. So it's measuring how fast the acceleration is changing. Paul's rate of change of his acceleration is 0. That means he's accelerating at a constant 10 meters per second squared. His acceleration isn't changing. You would feel that in a vehicle. You feel acceleration when your body is thrown backwards. But when you feel a constant pressure on your back, that's a constant acceleration. You're feeling that same constant pressure. Now, if you were in a, let's say a spaceship and that was launching off into space, you'd probably feel that backwards pressure. But then as your acceleration increased, you'd feel more and more and more backward pressure. That would be your acceleration getting faster and faster and faster, right? Acceleration can change. This is a measure of the change in acceleration. And now this is big because Quincy's acceleration was pretty small, -4 meters per second squared. But his change in acceleration was huge, -80. That means we must have caught Quincy at a moment when he was moving forward and he was touching the brake, but he wasn't just touching the brake, he was slamming on the brake, and you caught him when your body's flying forward in that slam, and then you feel even more and more forward momentum from that slam. We caught him just when he first started hitting the brake, and his foot is pushing that brake down, which is going to cause his acceleration, his negative acceleration to skyrocket. He's going to like slam on the brakes, and his deceleration from 125 is going to start going really quickly to 0. So he must have hit the brakes because that's such a big change in his acceleration. There is a name for that. A change in acceleration is called jerk. You can feel jerk when acceleration is big, right? Like when you accelerate, yeah, you're going to feel that. Like if you're in a car, you're going to feel that backwards acceleration. But if you slam on the brakes, you're not just being pushed forward, you're being jerked forward. You can feel a change in acceleration, and it feels like a jerk, which is why it's called jerk. That actually leads me to one of my favorite calculus t-shirts, which I'm going to show you in a minute. But you should probably make note that jerk is a measure of how fast acceleration is changing. It's a derivative of acceleration, the third derivative of a position function. Here's one of my favorite calculus shirts. Don't be a third derivative. Don't be a jerk. Right? Big third derivative is jerk. 3.5 is the derivatives of trigonometric functions. If you're curious, just because it's kind of fun and cool, we can actually go to greater rates of change than jerk, right? If y is position, y prime is velocity, y double prime is acceleration, y triple prime is jerk. There is a name for the next three, and it's kind of fun. There's a couple of names for 4, but one of the ones is snap. And even because one of the, right, if acceleration is, you can feel acceleration, then a rate of change of that is called jerk. An even faster rate of change how fast jerk is changing would be something that really happens fast. So they call it snap, right? After that, they're like, I'm running out of things to call it. So the next one, I'm not kidding you, is called crackle. And the third one, pop. Snap, crackle, and pop are the 4th, 5th, and 6th derivatives. Now you're not going to be tested on those, but they're kind of fun. All right. Trig derivatives, time for something completely different. We're going to talk about the derivatives of trig functions. Normally, I have students figure this out themselves. I'll have them graph sine on a graphing calculator, and then the derivative of sine on their graphing calculator so that they can kind of try to identify that. I'm just going to do that for you here. All right. So here we've got the derivative of sine of x. We should recognize that wave function. I'm going to graph y prime. So I'm going to call this sine of x. I'm going to call that f of x. And then I'm going to have my graphing calculator graph f prime of x. All right, f prime of x is there in blue. You might recognize that function. You might say, hey, that looks an awfully lot like cosine. Is it the derivative of sine cosine? If you're not sure, graph cosine. Same exact function right up the top. There's cosine, there's the derivative of sine. Turns out, derivative of sine is cosine. We can also go the other way around and try derivative of cosine. So here's cosine. Let's see if I can graph that. All right, there's cosine. I can graph g prime, the derivative of cosine. And many of you might have said, hey, it's going to be sine, but this isn't quite sine. It looks like sine, but sine goes up and then down and then up and then down. This one goes down and then up and then down and then up. This one is just the flip. This one is negative sine. If you're not sure, graph negative sine. There it is, right over the top. So while the derivative of sine is cosine, the derivative of cosine is not sine. The derivative of cosine is negative sine. So I'm going to go back to my other screen, and we're going to make sure we write that down because that is something you definitely need to have memorized. All right, so here's my note. d dx, don't forget that stands for derivative. The derivative of sine is equal to cosine. You are going to want to write that down, put it somewhere in notes that you can, like maybe a flashcard to memorize it, maybe put derivative of sine on one side and cosine on the other. you definitely need to have that memorized, right? On the AP exam, you're expected to have that memorized. If you don't have these things memorized, it's going to make the next sections really, really hard for you. So my words of advice for you today is spend some time actually memorizing these functions. Start to get them memorized. Derivative of sine is cosine. We've mentioned that. And the other one we had done was the derivative of cosine is negative sine. Definitely write those down somewhere in your notes. Make sure you memorize them. In fact, we're going to memorize all of the derivatives for trig functions. There are more derivatives than just sine and cosine. There's sine, cosine, tangent, cosecant, secant, and cotangent. 6 trig functions, so we have 6 derivatives to memorize. Before we, well, you know what, let's go ahead and do that first. All right, so here are all the trig functions and all the derivatives you need memorized. You're going to want to write them down somewhere because you're going to need them. Here's the ones we talked about already. Derivative of sine, that's cosine. Derivative of cosine, that's negative sine. Derivative of tangent is secant squared of x. Again, secant squared, that's a notation we should be familiar. That means the same as secant of x squared. Those are equivalent, right? So I like that notation. It makes it a lot easier. So those are the main 3, right? That's your main sine, cosine, and tangent functions. Their derivatives are cosine, negative sine, and secant squared. Cosecant. Derivative of cosecant is negative cosecant times a cotangent. The derivative of secant is secant times a tangent. And the derivative of cotangent is negative cosecant squared. Now, this might seem like a lot and hard to memorize, but after you spend a little bit of time, it gets easier. So definitely, again, put these on flashcards or something. You have to have these memorized. You gotta memorize these derivatives, because if you don't have them memorized, you're kind of like a fish out of the water. You're not going to be able to find the derivatives without these being memorized. So memorize these. It's not so bad to memorize because they kind of show up in pairs, right? Derivative of sine is cosine. Derivative of cosine, right? Sine and cosine is the exact opposite, but it's negative. Negative sine. Shows up here too with tangent. Here's derivative of tangent. There's derivative of cotangent. You're probably going to notice something here. Tangent is secant squared. Cotangent is negative cosecant squared. Same kind of pattern shows up with cosecant and secant. Derivative of secant is just that secant again times tangent. With a cosecant, it's a negative cosecant times a cotangent. So you could probably pair those up like that's color-coded. It might help you with memorization. All right, we're going to run through just some examples and why it's important to have them memorized. This one, find the derivative of y equals x to the third times sine of x. This is definitely a type of question that could show up in a multiple choice AP exam. And again, it's just kind of testing your memorized rules of derivatives. First one being, that's a product. So it's going to require the product rule. Y prime is going to be first, which is x cubed, times the derivative of the second. Well, I need to have that memorized or I'm stuck already and I can't do it. Derivative of sine is cosine. All right, so product rule. First times derivative of second plus second, which is sine of x, times the derivative of the first. Well, derivative of x to the third is 3x squared. So times 3x squared. Now, I could certainly leave my answer like that. I could put parentheses around here. It makes no difference. If I wanted to have nice math manners says you should normally put the variable first and the trig function second, because then you don't need those parentheses. So then I could write this. I could put that 3x squared first and the sine of x second, and then I don't need the parentheses. It makes sense either way. That's fine. Let's go to another example. Find the derivative of u equals cosine of x all over 1 minus sine of x. All right, testing our knowledge of derivatives. That's a quotient, so it's going to require the quotient rule. Quotient rule is low d high. So low is 1 minus sine of x. D high stands for derivative of the high. Derivative of cosine is negative sine. All right, minus high d low. So minus high is cosine. D low, well, the derivative of 1 minus the sine of x, that'll be negative cosine of x. Negative cosine of x, because here, if we had 1 minus sine of x, if that was my y prime derivative of 1 is 0, right? Derivative of constant is 0. I see this minus sign, so there's still a minus sign. Derivative of sine is cosine. 0 minus cosine of x, that's the same as a negative cosine of x. All right. So what do we have here? We got high here. We have high d low minus low d high, low d. We have low d high minus high d low, and it's all over low squared. So the low is 1 minus sine of x, and I have got to square that. All right. Typically, if you have something like this, you could leave it, but if it was multiple choice, the multiple choice answers would be simplified out. So we should see if we can simplify it. Let's give it a try. Multiplying that through would be negative sine of x plus sine squared. Negative cosine times a negative cosine would be plus cosine squared, all over 1 minus sine of x squared. This should look familiar to you. That's one of those trig identities we learned last year in pre-calc. Sine squared plus cosine squared is always, always, always 1. So I could even keep going further. And I could say u prime is the same as, well, that's negative sine of x plus 1, which I can write as 1 minus sine of x. Right, negative sine of x plus 1, 1 minus sine of x, same thing. The reason I like that is because it's all over 1 minus sine of x squared. So I say, hey, look at that. We've got a 1 minus sine of x there. We've got 2 1 minus sine of x's there. Those can factor out. This will cancel out with one of those ones. And my final answer is 1 over 1 minus sine of x, which looks a lot better than what I had before. That's the fully simplified version. Yep, it's a little bit complicated because I had to remember that this is a trig identity that is equal to 1. If you remember that, awesome. If not, I might want to take a look at your trig identities from pre-calc. As far as identities you should have memorized for calculus, that's probably the major one. Like you should know sine squared of x plus cosine squared of x equals 1. Like you should have that trig identity memorized from last year. Have it memorized still for this year for calc. There's a few other identities like tangent of x is sine of x over cosine of x, right? Your simple reciprocal identities, you should know that. Or like sine of x is 1 over the cosecant of x. So that's a quotient identity, a reciprocal identity. You should have some of those memorized. But this is really the big one that I sometimes see on AP exams. Again, not a lot, but if you have it memorized, it gives you one more question. All right. There was the derivatives we should have had memorized. I had one more example and another one there. I think this is getting a bit long. Let me read through this here. I'm going to work through this one, but if you're feeling short on time, feel free to skip that one. This would be a better one to do. So how about this? I'm going to do this one now. After this, you could call the video over because this one's so-so, I think, and do the problems. But if you want one more example, then you can see this one too. All right. So this one we should probably do. Find the equation of a line that is tangent to the graph of f of x equals 1 over x times tangent of x at x equals 2. So to find an equation of a tangent line, I need two things. I need a point and I need a slope. Find an equation of any line, I need those two things. To find the point, you just plug the 2 in, right? The point is going to be f of 2. Well, that'll be 1 over 2 times the tangent of 2, which we could put in our calculator and get a approximation if we like. By the way, you should make sure your calculator is in radians. In calculus, we always have our calculators in radians because these derivative shortcuts only work when we're measuring our trig derivatives. Sorry, when we're measuring our trig functions in radians. So you can have the trig functions measured in radians or in degrees. The calculus behind what we're memorizing only works when we're measuring radians. So in calculus class, we always have our calculators set to radians. If I plug that in, this will equal negative 1.093. So that means I've got a point of 2, right, from my x value, comma, negative 1.093. That's the point I'm dealing with. F prime gives me slope. I could use a calculator and just find f prime with a calculator, but the whole point of this is memorizing my derivatives, so I should be able to figure that out by hand. You know what? I'm not going to worry about that one. Let's have that one be a calculator allowed. All right, so I've put f of x equals 1 over x tangent of x here. It's that crazy looking function. I've double checked that I'm measuring in radians. I am. I wanted to know what f prime of 2 was. So I'm going to put f prime of 2, 3.433. All right, so f prime of 2 was 3.433. So the equation of my tangent line is going to be y minus the y coordinate. So y plus 1.093 equals the slope, 3.433, times x minus the x coordinate, x minus 2. There we go. That's doing it with a calculator. We could do it without a calculator as well. It would require the product rule, right? First times derivative of the second plus second times derivative of the first. But for this problem, I think I'm just as happy with a calculator. That would probably be a calculator allowed problem. All right, last example. This one says, show that the derivative of cosecant is negative cosecant times cotangent. That was shown right here. Right there it is. But it says, show that it is by finding the derivative of 1 over sine of x. The reason we should know that works is we should know that cosecant of x is the same as 1 over sine of x, right? So if we can find the derivative of 1 over sine of x, it's going to be the same as the derivative of cosecant. So let's say y equals 1 over sine of x. Let's find y prime. Well, that's a quotient. So if I wanted to do the quotient rule, it's low d high minus high d low. So low is sine of x. D high, the derivative of 1 is 0, right? Derivative of constant is 0. Minus high d low, high is 1, times the derivative of sine is cosine. All over low squared, so all over sine of x squared. Just about. This was 0, so that's gone. So I end up with a negative cosine of x all over sine of x squared, which I can write as sine squared of x. However, I wanted to show it was equal to this, so I got to go a little bit further. Maybe you're seeing that there. I can split this up as a negative 1 over sine of x times cosine of x over sine of x. Right, taking that sine squared, sine times sine is sine squared. And taking that negative cosine and putting the negative 1 here and the cosine there, so I just split it up. But the reason splitting that up is nice is because this you should recognize. 1 over sine of x is cosecant, so that's going to be a negative cosecant because that's a negative sign right there. Times cosine over sine, that's our quotient identity for cotangent. So all that stuff we learned in pre-calc about those rules, we made you memorize them. Those different identities that you memorized, they're all coming back. All right, there's your assignment. Give it a try. I am going to include a PDF of some important identities in the Schoology folder, because a lot of us might not remember those identities, and they're definitely going to be important to have memorized. You're not going to need all of them, but I will include a PDF of the identities you should have memorized for calculus. So in pre-calc, you had a whole big sheet of identities that we used. In calculus, we have a smaller subset, but you're not allowed the sheet. You have to have them memorized. I will include that sheet of identities you should have memorized in the Schoology folder with this homework assignment. See you later.